Hello and welcome to the fourth and final part of the Mathematics Survival Guide. In this final part of Lesson 2, we're going to briefly examine complex numbers and remind ourselves of some important relationships that exist, in particular the link between complex numbers and trigonometric functions. Complex numbers also have a very applied use on this course. They allow the easy quantification of phase differences, which is information that we use when characterizing the oscillatory rheology of viscoelastic materials. So we're going to start by examining a generalized version of this example before moving on to examining the properties of complex numbers, revising Euler's formula, and examining some of the results that Euler's formula predicts. So let's start by giving a bit of motivation. We're going to see in later lessons that complex numbers are very, very useful to allow us to easily analyze phase differences in harmonic systems. This means oscillatory systems. There, of course, we can examine these phase differences simply using trigonometric functions, but complex numbers just allow us to do it that little bit more easily, so why not use them? So let me give you a generalized example of the sort of scenario we'll be looking at later, and then what we'll do is we'll move on to revise some basic properties of complex numbers. So here on the blackboard I've put a big pink box, which I'm just calling an engineering system of some sort. This engineering system has as input a sine wave, there in yellow. Let's say that this engineering system is quite simple, and since we have a pure sine wave input, there's no harmonics to it, there's a pure sine wave output. The only things that have changed in the output with reference to the input is that the amplitude might have changed a bit, and the phase may be offset from the original phase of the input signal. If you look at the blue signal, you can see that at 0 time, the amplitude is non-zero, so it's somewhere up near whatever full amplitude is. Whereas for the yellow signal, at 0 time, we've got 0 amplitude. So that's an example here of a phase lag. So very often, with these engineering systems, information is contained in that phase difference. And it's not just rheology that you find this in. If you talk to electrical engineers, they deal with systems with sine waves a lot. Alternating current, after all, is a sine wave. And they use complex numbers a lot to quantify these systems in terms of performance when they're thinking about resistance and inductance. So let's just zoom in on that signal. There I've plotted the input signal overlaid onto the output signal, the input in yellow, the output in blue. The phase difference is simply the gap, the difference between the two peaks of that input and output, as I've just labelled there. So if our input signal is I of t, and our resultant output signal is r of t, we could simply write I of t as a sine omega t. A here is the amplitude of that sine wave. Omega is our angular frequency. And we've just said it's a sine wave. So I of t is a sine omega t. We mentioned that because there's no harmonics other than just the fundamental frequency in that sine wave, the output will also be a sine wave. It's a simple engineering system. We acknowledged that the amplitude might change, so the amplitude of the resultant signal r of t is now b, and the phase might have lagged or leaded a little bit. So I've got the same frequency, omega t. However, I've got omega t plus delta, where delta now is that offset that I've labelled in the graph between the two peaks of the respective signals. Now, if you recognise these two expressions, that I of t could also be written as the imaginary part of a e to the omega t, and that the resultant signal r of t can be written as the imaginary part of b ei omega t plus delta, then you probably know everything that I'm going to cover in this part of this lesson. However, if what I've just said is a little unfamiliar, maybe it's been a few years, or you just have never come across that expression before, then do watch on. So, the fundamental motivation here is that complex numbers can be used to represent the behaviour of harmonic systems, which is what we're going to be doing later in the course. But in order to represent the behaviour of harmonic systems, we need to know the basics of how to use complex numbers, how to manipulate them, and we also need to know one very important identity that allows us to link exponentials to trigonometric functions. So that's what I'm going to cover now. Now, let's say we have an arbitrary complex number, a plus ib. Now, a is a real number. It's the sort of numbers we use in everyday life. 1, 2, 3, pi, that sort of thing. We can easily process what that is. Now, the imaginary part, IB, involves the square root of -1. Now, we know ordinarily we can't take the square roots of negative numbers, but the assumption in complex numbers is that the square root of -1 exists. It's what we term an imaginary number, and once we've made that definition, we can then handle things that have negative roots. So I here is the square root of -1. For the electrical engineers, that would be J, because I means current. And a real number plus an imaginary number is what we term a complex number. So A plus IB is a complex number, A is a real number, IB is an imaginary number. Okay, so we're just going to accept that as a definition. And what we really want to do is to remember how to manipulate complex numbers. So let's do this by means of an example. Let's say I have the product of two complex numbers. So the first is 3 plus 2i, the second is 5 minus 7i, and I know the result is going to be complex, but we don't know yet what the complex number will be. So we've just set the result equal to an arbitrary complex number, a plus ib. What we want to do is to find a and to find b. So the way we do that is quite straightforward. We multiply the bracket out. So we've got 3 times 5, 15, that's real. Then we've got minus 21i plus 10i, which gives us minus 11i. Those are terms in blue. That's the imaginary part. Then we have 2i times minus 7i, which gives us minus 14i squared. Now, I've written that in pink because we know that I squared is equal to minus 1. Therefore, terms in I squared are real. Minus 14i squared is just simply 14. And so we add that 14 to 15 to get to the 29, which is our real number, and the minus 11i is our imaginary part. And so we can therefore say that a plus ib is equal to the product of those two numbers, where a is 29 and b is minus 11. So operating on complex numbers together is quite simple. The key rule to remember is you can treat real parts and imaginary parts separately, but imaginary numbers can be converted to real numbers if you've got even powers of I squared, I to the 4, I to the 6. So I squared is equal to minus 1, so therefore any terms in I squared simply revert to being real. But remember that sign change. So hopefully that gives you a little bit of a reminder on how to use complex numbers. Let's now look at a very, very important identity. And this allows us to do the phase analysis that we're going to do in later parts of this course. Now, Euler's formula is quite a remarkable piece of mathematics. It was dreamt up by a chap called Leonhard Euler in the 18th century. He was a Swiss polymath. And Richard Feynman, one of the most renowned physicists of the 20th century, said that Euler's formula is the most remarkable formula in mathematics. And it states thus: e to the I theta is equal to cos theta plus I sine theta, where we remember I is the square root of minus 1. Now, at first sight, one could quite easily say, how on earth does that relationship hold? How can we relate exponentials to trigonometric functions? There's quite a long answer to that, and I'm not going to go into that here because it would be a diversion. However, what I can say is if you take Taylor expansions of the left-hand side and of the two terms on the right-hand side and sum the series, you'll find that they're identical. And there's some very, very nice, elegant explanations that you can find in the literature, but I'll leave that as an exercise for home reading. What we just need to accept is that this formula is true and that we can use it to relate trigonometry to exponential behaviour. And we'll see why that's useful in a minute. What we can also do with this is prove some results that we already know, and it's a remarkably adaptable formula. So let's do that latter part. Let's prove some results we know. Let's look at the left-hand side in terms of its derivative. Let's say what we have is a function e to the I omega t. We will see functions like this later on in the course, and we take its differential with respect to time. We know we can do that really easily. It's just I omega e to the I omega t. So we've taken the time derivative of the left-hand side of Euler's formula. That has to be equal to the time derivative of the right-hand side, doesn't it? but we can work out what that is, because if we look at I omega e to the I omega t, we can apply Euler's formula directly to the e to the I omega t bit. So that becomes I omega, in brackets, cos omega t plus I sine omega t. If we multiply that through, we have I omega cos omega t, that's imaginary, plus I squared omega, so minus omega sine omega t. So there, the bottom row in orange is the result of differentiating e to the I omega t and substituting in Euler's formula. But now we've done that, we can compare that to the time derivative of cos omega t plus I sine omega t, which allows us to remind ourselves what the differential of cos omega t and sine omega t is. And what I mean by that is just look at the real parts and look at the imaginary parts. Inside the dt by dt term at the bottom of the board, you've got a real part, cos omega t. So the real part there, its time derivative is going to be the real part of the line above. So if we're differentiating cos omega t, it's simply minus omega sine omega t, which of course we know from basic calculus, but sometimes we might forget whether it's positive or negative. Likewise, if we can't remember how to differentiate with respect to time sine omega t, we just look at the imaginary parts. The imaginary part within the d by dt bracket is sine omega t, that's what we're differentiating. The result on the line above is omega cos omega t. So there we go, we can prove to ourselves, using Euler's formula and complex numbers, what the derivative of cos omega t is with respect to time, and the derivative of sine omega t is with respect to time. We can also do a few other things as well. So let's prove some trigonometric relationships that you might remember from the dim and distant past. Let's say I use Euler's formula thus. On the left-hand side, I'm going to say e to the I theta is a term where theta equals a plus b, where a and b are just arbitrary real numbers. And so I have e to the I, a plus b. That has to equal to cos theta plus I sine theta, so it's cos a plus b plus I sine a plus b. And here's the root of what you might remember. So what we might want to do is to prove to ourselves what cos a plus b equals to, and what sine a plus b equals to, because we know there's some identities here that we can employ to operate on those terms more easily. But let's just say we've forgotten them, and we might want to derive them from first principles. So we can do this. Let's look at the left-hand side first, that e to the I a plus b. I know, using the rules of expanding exponentials, that e to the I a plus b is simply e to the I a times e to the I b. And incidentally, this is what allows us to analyse phase leads and phase lags very easily, because we're expanding things along the lines of e to the I omega t plus delta, and so we can simply just condense them into the product of two exponential terms. So e to the I a plus b is equal to e to the I a times e to the I b. So let's write that out now using Euler's formula. We know e to the I a is cos a plus I sine a. E to the I b is cos b plus I sine b. Let's multiply these two brackets out. That gives us cos a cos b minus sine a sine b as real parts, and cos a sine b plus sine a cos b as imaginary parts. So we can compare the real parts from the first line, cos a plus b plus I sine a plus b. If we compare the real parts of cos a plus b to the real parts in the formula that we've just derived, we can see that cos a plus b is cos a cos b minus sine a sine b. So you might recognise that as a cosine rule. Likewise, if we think about the imaginary parts in blue, halfway up the board, sine a plus b, what does that equal to in terms of an expansion? Let's look at the imaginary parts of the formula that we derived. Well, it's cos a sine b plus sine a cos b, which again is a sine rule that you all know and love. So Euler's formula and complex numbers can help us prove that as well. So that's all I want to go over in terms of complex numbers, because that's pretty much all we're going to use in terms of complex number theory. But we are going to use it, and you do need to know it. So the point of this lesson was to remind you that complex numbers are an essential analytical tool in physics and engineering. We're going to be using them to find phase differences and hence material properties when we come to study the art of rheometry, which is measuring the response of unknown liquids. Remember, When dealing with complex numbers, real and imaginary parts are equated separately, and if you get I squared is simply -1, and that is converting an imaginary number to a real number. Just watch the change of sign. What I've done in the last few bits on the board here is to remind you that complex numbers can also be used to simplify differentials, which is the key use that we'll be putting them to, and they also contain trigonometric rules, which is another key use that we're going to be putting them to.